Okay, so let's talk about games. In this chapter we'll talk about strictly determined games. Now, of course, games are many types and there are many descriptions. In this particular chapter and in this book, we're talking about games with two people played against each other, competitive games. And these are games which have a payoff, an amount that's a payoff. Right, so it's not win or lose, it's you get a certain amount, like gambling games, something like that. But they are two players, competitive games, and you'll see how we set these up mathematically. So here, game theory in mathematics considers situations in which there are two or more persons, each of which controls some or not all the variables necessary to determine the outcome. That means that I can influence the outcome, my opponent can influence the outcome, but we can't determine it completely, either one. The outcome depends on what you do and what your opponent does. Okay? Depending on which event actually occurs, the player receives various payments. Okay, so again, depending on what you do, what your opponent does, you receive a payoff. There's no chance in this. If you know what you do, what your opponent does, that's what you get. So it's not a spinner game or some other kind of game where there's a chance element. Okay. If for every possible event the algebraic sum of payments to all players is 0, the game is called zero sum. Otherwise it's non-zero sum. All that means is that in this competitive game, what I win is what the other one loses. So basically, I pay the other person, or that other person pays me. But the sum of my payment to him and what he receives is 0. That doesn't mean it's a fair game. It just means that the payments, my benefit is his loss and vice versa. Right. Usually the players will not agree as to which event should occur, so their objectives in the game are different. So obviously that's going to be true. If what I win, then he loses. Right. So he's going to want to win as much as he can, and I'm going to want to win as much as I can. Okay. All right, so the solution is based on the principle each player tries to choose his course of action so that regardless of what his opponent does, he can assure himself of a certain minimum amount. Now, this idea takes some thinking about. This idea that whatever the opponent does, you want to assure yourself, here, I'm going to highlight this here, of a certain minimum amount. In other words, you want to get the best possible worst case. This is also called a max-min strategy, which means you want to maximize your minimum benefit. Now, you can think about whether this is a reasonable assumption. Remember that your opponent is going to try to minimize your gain because minimizing your gain will maximize his gain. So it makes sense that you want to limit the maximum possible benefit that your opponent is going to make. Your opponent is going to always try for the maximum benefit. So you should try to accommodate that predisposition that he has, that he's going to try to get the best possible result, and you should counter with a strategy that limits his best possible result to be as small as possible. And if you do that and he does, then he should also do it if he's an intelligent player. So you both play in this way that you want to maximize your minimum gain. All right, so matrix games are discussed in chapter 8 through 11. We shall not discuss non-zero sum games in this chapter. Okay, let's go on. So most recreational games such as tic-tac-toe, checkers, backgammon, etc. can be viewed as games as strategy. Gambling games are betting against the odds. So in this and following sections, we shall formulate simple games that illustrate the theory and are amenable to computation. We shall base these games on applications in business situations and on recreational games. In fact, the application of mathematical game theory is very important in economics, and some of the originators of the theory won the Nobel Prize for economics because you can think of business as a game. My company, his company, my competitor, and I'm his competitor. So you want to do whatever you can to maximize your profit. So this is similar to some of the linear programming situations we've talked before about maximizing profit. Okay, so let's take a look at one of these business games. You have two stores, R and C, which are planning to locate in one of two towns. As in figure 49, town 1 has a 60% of the population, town 2 has 40%. If both stores locate in the same town, they'll split the total business of both towns equally. But if they locate in different towns, each will get the business of that town. Where should each store locate? All right. Now, before you get caught up in the mathematics of the problem, just think about this from a practical point of view. If you are a store and you want to locate, and one town has 60% and the other has 40%, then where are you going to locate? Well, it would make sense that you'd locate in the town with more people. But your competitor is going to think the same way, right? So you have to take that into account as well. The fact that your competitor is thinking the same way, does that change your strategy or not? Well, the payoff is determined by this. If both stores locate in the same town, they'll split the total business equally. But if they locate in different towns, each will get the business of that town. Right? So we can set up the alternatives as a matrix, kind of like the linear programming data box that we had before. The options for store R are to locate in town 1 or town 2. The options for store C are to locate in town 1 or town 2. All right? If both stores locate in town 1, the payoff is 50. If store R locates in town 1 and store C locates in town 2, then store 1 gets 60% of the business. So that means that this 60 refers to store R's payoff. All right? So all these numbers refer to store R's payoff. Now if store R gains 60%, that means store C loses 60%. So here's where you have the zero sum. Whatever is store R's gain is store C's loss. All right. Similarly, if store R locates in town 2, he gets 40% of the business, and that means that store C loses 40%, but he gains 60%. Right? So, and if store R and store C both locate in town 2, they both get 50%. Okay. All right. So this is a game situation. Since each store can control where it locates, but cannot control where the competitor locates. All right. So this tells the same description of what I just said, and we have this so-called payoff matrix in figure 50. Okay. And here it says the same description of what I said, that these are the percentage gains of store R and the percentage losses of store C. Okay. So how should players play this game? Now you can think of this one by one. So think of it from the point of view of store R. Store R says, okay, if I choose location 2, well, let's think about this. I mentioned we're talking about max-min strategies. So I want to maximize my minimum gain. So his gain are these values. Now if he goes in location 2, there's 40 and 50. Right? So his minimum gain is 40. On the other hand, if he locates his store in 1, his minimum gain is 50. So from that point of view, he's going to locate in town 1. Okay. Similarly for store C, if he locates in town 2, these are his losses, right? His minimum loss is, rather I should say, his minimum gain is the same as his maximum loss, right? Because his gain is the negative of his loss. So his minimum gain is his maximum loss. Here is his maximum loss, which is 60. On the other hand, if he locates in town 1, his maximum loss is 50. Right? So from that point of view, store C will prefer 1 over 2 because the worst he can do is lose 50% of the business. He could possibly lose 60% of the business here, and most likely because store R knows the score also and knows the situation, he's going to choose row 1. He's going to choose row 1 because that ensures his best payoff. Right? So both of them are going to choose row 1 from that point of view, and they'll both end up with 50%. Which is a reasonable outcome, and in fact is the outcome you would have expected at the beginning, even while thinking from a game theory perspective. All right, so in this simple case, our result agrees with intuition. Later on we'll have cases that are not so simple, and you'll be able to solve games that we never could have solved using intuition. Okay, so let's move down. Let's go on. All right, so that pretty much encapsulates this discussion here. You can read that for an alternative description. And in general, we can describe this situation. We described that previous game as a matrix, and we can describe any game in this type, as a matrix. Here we have an m by n matrix where m rows and n columns, and each row represents a possible strategy of player R, who's called the row player, and each column represents a possible strategy for the column player. They don't necessarily have to have the same number of strategies. But in each box in the matrix, you're going to have a payoff, and that will be the payoff for row R, which is the negative of the payoff for row C. Now, these numbers could be positive or negative, doesn't matter, but just remember that the numbers in the box, like these numbers here, are the payoff for row R, and they're the loss or negative payoff for the player in row C. Right, so, as it says here, Gij is going to be the payoff if player R chooses strategy I and player C chooses strategy J. Right? All right, here's another example of a matrix game. All right, here we don't have a practical situation associated with it. We just have the numbers. So the question is, what's the best strategy for R and the best strategy for C? So here's kind of a thought process. Player R would like to get the 5 payoff. That's his biggest possible payoff. But if he goes for this one, then the column player is going to choose 2. He's not going to sit around and let the row player get the 5 payoff, and he's not going to be dumb like that. He's going to choose 2. He's not going to let player 1 get his most benefit. He's going to try to get his most benefit himself. So that's really not a good option for player R to choose the first row, because he's going to get burned. It's better for him to choose the second row. Okay. In this case, his maximum payoff is less, but what he stands to lose is also much less. All right. And player C, well, look, player C would want to get his best payoff here anyway. Now, he's not going to get his best payoff, but at least he's going to get something that's not so bad. So we'll both end up with 0. Okay. So here's another case where we have what's known as a strictly determined game. The row player is going to choose the row where he maximizes his minimum benefit. In row 2, his minimum benefit is 0. In row 1, his minimum benefit is -10. So he's going to choose row 2. Player C is going to choose the column that maximizes his minimum benefit. His minimum benefit here is represented by the 2. Sorry, is represented by the 5. Is represented by the 5 because that's his maximum loss. His maximum loss is his minimum benefit. And in column 2, his maximum loss is 0, so that's his minimum benefit. Okay, so the maximum, how can I say, the maximum minimum benefit of the row player is the same as the minimum maximum loss of the column player. I think I said that right. Well, you can figure it out if I'm pretty sure I said that right. You can rewind the tape and make sure that I said it right. Okay. All right, so the solution in the first two examples have the following in common. In each case, the value is an entry that's the minimum of its row and the maximum of its column. Let's go back and verify that. In this case, it was certainly true. The minimum of row 2 was 0, which is the maximum of column 2. And back here for the first one, the minimum of row 1 was 50, which is the maximum of column 1. So these are so-called saddle values. And it turns out that if a game has a saddle value, then following this strategy where I want to maximize my minimum benefit, where player R wants to maximize his minimum benefit, and player C tries to minimize his maximum loss, they'll both end up choosing the same entry. Okay, those entries will agree, and that's called the saddle value. That saddle value will end up being the payoff in such a game. Okay. When such a saddle value exists, it's always the value of the game, and the game is strictly determined. Okay. Now let's run through this argument. To see this, consider any game G where there's an entry Gij equals V, which is a saddle value. Since V is the minimum of row I, R can play row I and assure he will win at least V, right? Because it's the minimum. And since V is the maximum of column J, C by playing column J can assure that R will not win more than V. Okay. So, in other words, if C plays a different column and not this optimum column, then the row player will make off better, because every other entry in that row gives a better payoff than the entry in column J. On the other hand, if the row player is not smart and doesn't play row I, then C can make off better than V, because the payoffs in that column, in the column J, are the least favorable one is the one in row I. So if either one does not choose this optimal strategy, then the other player can take advantage. Right? So this is the one that really balances the benefit between both the row player and the column vector, column player. All right. So to summarize, let's follow this definition. Consider a matrix game with payoff matrix G. Entry Gij is said to be the saddle value if Gij is simultaneously minimum of ith row and the maximum of the jth column. If the matrix G has a saddle value, it's said to be strictly determined. The optimal strategies are: for player R, choose the row that has a saddle value, and for player C, choose a column that has a saddle value. The payoff will be the saddle value entry. And the game is fair if the saddle value entry is 0. As I said, you can have a zero-sum game that's not fair. That if they play repeatedly, one player will get a benefit. But as I said before, a zero-sum game, the one player's benefit is the other player's loss. Now, so far we haven't proven that there's not more than one saddle value, but in fact there is only one possible saddle value. And that's proven in the exercises. All right. So here, let's consider another case where we have 3 towns, and these 3 towns are listed here. These numbers in the town give the percentage of the total population. So 50% of total population in town 1, 30% in town 2, and 20% in town 3. Now in this case, the rule is that the customers will go to the closest store. So for instance, if one store locates here and one store locates here, right, then of course the people in town 1 will go to the store that's located here. People in town 3 will go to the store that's located here. What about the people in town 2? Well, town 2 is closer to town 1 than to town 3, so they'll go to the people in town 2 will go to town 1. Suppose the 2 stores locate here. Suppose R store locates here and C store locates here. Well, in this case, then how about the people in town 3? Well, the people in town 3 are going to go to the closest store, which is here. All right? So if we have one store here and one store here, then the store in town 1 gets 50%. The store in town 2 also gets 50%. Now you also see if you have both stores locate here, then of course both stores will share the revenue equally. Customers will be equally likely to go to either one. So if both stores locate here, each store gets 50%. If one store locates here, the other store locates here, each store gets 50%. So it seems like there's probably 2 solutions that give me the same payoff. Let's see how this works mathematically. Well, you can verify that this payoff matrix follows the rule that I was saying. For instance, this 80 says if store R locates in town 1 and store C locates in town 3, well, that's as I said, if store R locates in town 1 and store C locates in town 3, then the people in town 2 are going to go to the store in town 1. So that's going to be 50% plus 30% gives you 80%. Now you can verify all of these numbers correspond to the situation shown above. This 20%, store R locates in town 3, store C locates in town 1. 80% are going to go to the store in town 1. Right. So let's think about our max-min strategy. Where's the minimum payoff in each row? Well, here we have the minimum payoff in this row is 20. Minimum payoff in this row is 50. Minimum payoff in this row is also 50. And columns. Minimum payoff in this, the maximum loss in this column is 50. Maximum loss in this column is 50. Maximum loss in this column is 80. Right? So it looks like store R is going to choose one of these two rows. Store C is going to choose one of these two rows. In both cases, they'll get 50. No matter which choice R makes, which choice C makes, they'll both get 50%. Right? So in fact, we could employ what you might call a mixed strategy. The role player could flip a coin. He could say, okay, I'll flip a coin 50-50. 50-50 I'll locate in town 1. 50-50 I'll locate in town 2. And that would mean that we place a weight 1/2 on town 1, weight 1/2 on town 2, weight 0 on town 3. So these numbers would represent probabilities. If he used that strategy, he'd get 50% of the business. Or he could do a 20-30 coin, or do a flip up, or throw a dice or something. If you throw a dice and you get a 1, then he locates in town 1. Otherwise, he locates in town 2. In that case, A would be 1/6. 1 minus A would be 5/6. So no matter what A is, this strategy of choosing town 1 with probability A and town 2 with probability 1 minus A is going to give him the same payoff. Okay. Similarly, for the column player. Okay. The column player could do the very same thing. So here we represent the column players by a similar strategy that's a column vector. Now, why do I represent the player R's strategy with a row vector and player C's strategy with a column vector? Well, it turns out if I take this matrix up here and I multiply on the left by this strategy vector, I'm going to get my payoffs. For instance, if I take the row vector 1, 0, 0 and multiply this matrix on the left by 1, 0, 0, you can verify that the result will be 50, 50, 80. Okay? And that's the strategy, that's the payoff that player R will get if he uses the strategy 1, 0, 0. Similarly, if I multiply it on the right by a column vector, that gives me the payoff for the column player related to that strategy. For instance, if I take the column vector 1/2, 1/2, 0, and you multiply this matrix on the right by that column vector, then you can work out that the result will be the expected payoff to the column player, the expected loss of the column player for the different possible options of the row player. Right? So the multiplication of this matrix by either the row vector or the column vector has a significance of the expected payoff of that strategy. And we'll get more into that in later chapters. So if you didn't quite get that, just file it away and we'll talk about it later. Right? So one more example. Here we have a payoff matrix. In this case, the row player has 3 strategies. The column player has 4 strategies. And you can identify the max-min strategies here. The minimum here is 1. Minimum here is -9. Minimum here is 1. So both row 1 and row 3 have a minimum of 1. On the other hand, for the column, the maximum loss here is 1. Maximum loss here is 12. Maximum loss here is 1. Maximum loss here is 7. So player C has columns 1 and 3. So the role player plays any combination of strategy 1 and strategy 3, and the column player plays any strategy and any combination of column 1 and column 3, they're both going to get a payoff of 1. You can see 1, 1, 1, 1. No matter which of those options they choose, they're both going to get a payoff of 1, and that's the value of the game. All right? Very good.